Welcome to CSIS. It stands for Cryogenic Superconducting Inertial Sensor. I'm Joris van Heijningen, a research scientist at UC Leuven, and I'm here to tell you about the benefits of developing such a sensor for terrestrial and lunar gravitational wave detection. So first, I wanted to take you back to 2015, when we had the first detection of gravitational waves. And made this movie. So here you see these two black holes revolving around each other, merging into one, sending out a pulse of gravitational waves, which in the first case of 2015 traveled for 1.3 billion light years, making the Earth stretch and squeeze. Of course, here the scale of this effect is vastly exaggerated, because you need detectors like LIGO, which are this kilometer scale interferometers, to convert this stretching and squeezing into these flashes of light that you see there. So you saw this stretching and squeezing of the arms, which could also say make the mirror move, but they make the mirrors move at this tiny percentage of the Earth's usual ever-present motion. So if you put this mirror on a frame on the Earth, you're never going to measure anything, because your detector will be just swamped by the Earth's ever-present motion. So you need to do something about that, and we have a way of decoupling it. The mirror from the Earth's motion, and we do that by suspending it. Of course, the systems that we use are a bit more advanced, but for argument's sake, we can look at this simple thing of just a simple pendulum. So here you see these mirrors, and at low frequencies, you see that they will just follow the motion of the input motion, in our case, the Earth's motion. Then there's the resonance frequency at a certain frequency that depends on the length of the pendulum. But this is a price we have to pay to get it into this regime of attenuation, where the mirror moves less than the Earth. And you can see that here, if you have high frequency motion at the top, the mirror will hardly move along. The higher the frequencies, the less it will move along, actually. Of course, we don't want to pay this price, so we have sensors to help us dampen this motion. And of course, we don't use one single pendulum, but we make this whole chains of pendulum. So in the case of Virgo, for example, here you see the mirror at the bottom of this 9-meter contraption, which is suspended via a chain of pendulums with in between other elements that have vertical blades and springs, etc. But these systems, if you have multiple pendulums, you get more of these peaks, but then you get a steeper slope downwards and more decoupling. And this whole system is in vacuum, so this is in a vacuum tank, and of course there are more structural elements that could have internal modes that then end up here and ruin your nice decoupling. So we also need sensors to monitor this region. And of course, the steeper the slope, the more sensitive your sensors should be. So at some point, commercial sensors were not good enough anymore, and we needed to develop our own. So for another suspension in Virgo, for the optical benches, during my PhD at NICEF, we developed this sensor, where you see here a Watts linkage, which is a type of a suspension of suspending the proof mass inside the frame. And we do that in a clever way with an inverted pendulum and a pendulum, such that we can make the resonance frequency of this system very low and make this proof mass not follow the frame from quite low frequencies onwards, such that the relative motion between the proof mass and the frame can then be read out by in this case, interferometric readout. And then you're in business. Then you're just measuring because the proof mass is not moving, you're just measuring the frame motion, and the frame motion is equivalent to the optical bench, and that's the thing you wanted to monitor. So in this schematic, we can see a bit better what's happening. So the proof mass has a mirror attached to one side, which is part of this interferometer. And this interferometer is both arms are read out using this extra beam splitter, the top beam splitter, so that we can subtract these two signals and get rid of all the common mode noise, like laser frequency noise, etc., such that we can get this very clean error signal. Now, this error signal is then sent to an actuator. It's called a voice coil, but it's a coil magnet actuator. And this coil magnet actuator actually then locks the proof mass to the frame. And we have to do that to keep the interferometer in a certain working point, because else it will either lose its lock and no longer be linear anymore, or this nice subtraction of all the common mode noise actually doesn't work. So this signal that is sent to this actuator to keep the proof mass in one place is then the output of the sensor. So this is the best result that we got. Here you see frequency from about 0.3 hertz to 100 hertz, and the displacement from femtometers to about a micron or so. And you can see what we did was put this new sensor, the NICAF accelerometer, put it next to a commercial sensor, in this case the Sercel L4C, and measuring the motion or looking at the motion that they were measuring. So you see that both of them are measuring the same, so that's good. We know that we can trust these traces, more so because the right where we expected, the commercial sensor hits its own noise floor, and then the blue sensor goes on to reach this 8 femtometer per root hertz level from 30 hertz onwards. What happens here, we don't fully understand, but this is a nice result. Still, I have mixed feelings about this result, because, of course, this is nice, because below the green line, which is the best sensor used in gravitational wave detection in LIGO, the Geotech GS13, yeah, we perform the best inertial sensing in the world, but it's not where we model, and so I think this has to do with still some residual motion that we aren't able to get rid of the proof mass. And another thing, if we want to be better at low frequencies, which is interesting for future gravitational wave detectors, as we shall see, we have to get the thermal noise down. And the thermal noise goes down, of course, with temperature, but also with the quality of your suspension. So the suspension is of quite good quality, but it is spoiled by this coil magnet actuator, because we have a magnet next to moving metal parts, and this gives eddy currents, and they cause eddy current damping, and they make the Q go so low and increase the thermal noise, swamping the low frequency area. So we want to change that. First, less residual motion, so we want to use these Rasniks. Now, Rasniks work the way that you have a light source, a simple LED. They project this checkerboard mask via a lens on a pixel sensor, which could be a simple webcam. So if you now fix the lens and the webcam and the light source well, we'll see to, for example, the frame, and you fix this mask to the thing you want to know the motion of, in this case the proof mass, then you have a displacement sensor. And this is very long range, because you can make this mask as big as you want, and you can still obtain these very nice displacement sensitivities, as you can see here. So here you see frequencies down to quite low frequencies, really 50 millihertz or so, but it's supposed to be flat down to arbitrarily low frequencies. And you can see that we reach 7 picometer per root hertz, and we even think we can get below a picometer. So that would be nice to take out the proof mass resonance frequency and make the residual motion go less. And another thing is changing the coil magnet actuator. So instead of the coil magnet actuator, we have this superconducting coil, and this generates a magnetic field which sees a superconducting surface. And this, because of the Meissner effect, it will go around it and exert some sort of magnetic pressure on this surface. And so we will have a push only actuator, rather than this was a push and pull. Yeah, we can use this as an actuator in our next sensor. So a postdoc, Elvis, in my group is collaborating with the University of Namur, simulating to get the optimal geometry, and going there to make use of their deposition setups to deposit these nice spirals. So what does that bring us? It will bring the same Watts linkage, now with these two actuators. Also the the interferometric readout that has had a slight change, because now we use polarization optics. And this is nice because we can make all the light go to the photodiodes rather than being dumped, which in cryogenic operation is of course a good idea. We work together with the Catholic University of Leuven to bring us a very low power consumption, very low noise readout chips. And as I said, we use the Rasnik in order to take out the proof mass mode. This is all done in niobium, and we are making our first steps. So here you see another postdoc in our group, Francesca, building this interferometric readout. What is this all? What will we use these sensors for? One of them is the next generation gravitational wave detector, so the Einstein telescope. Here you see this triangle. These are 10-kilometer long arms where 6 interferometers about 200 meters underground will operate. 3 of those interferometers will be cryogenic, so the blue parts that you see here, and that's optimized for very low frequency. So their suspensions look a bit like this. So here you're looking from where the beam is going. So this part here from the side is really only to get the cooling power without much vibration at the mirror. And so it would be good to place the sensor here to see if everything's going all right. So what kind of sensitivities are we seeing? Here in dashed gray, you see the sensitivity for modeled during my PhD. And we see that if we go cryogenic and superconducting and with a Rasnik, we see that we can make quite an improvement. If we go on to silicon, that the improvement can be even better. And you can see we really get to femtometers or so below 1 hertz. And that's good because we need to monitor what is going on at the near the mirrors. So you have the mirror, and then it's suspended at a platform above that mirror. And if you put these sensors on the platform above that mirror, then you have a good way of monitoring if this cooling procedure is going well. So now we say goodbye to Earth and go to the moon to see what happens if we put these sensors on the moon. So the moon, just like the Earth you saw in the movie, also wobbles when a gravitational wave passes by. So if we now put these seismic sensors on there, then the moon is so quiet because it doesn't have oceans or tectonic plates that we can actually directly measure these gravitational waves. We want to do that cryogenically, and if you put them on craters on the south or north pole, then you get these places that have permanent shadows. So you see, for example, you can get a natural cryostat below 40 Kelvin. If you want to know more about this, there's our publication, quite recent. And if you want to join, then be sure to send me an email because we need more people. And so what are we aiming for? So we're aiming to bridge a gap between LISA and ET. LISA is a kind of a triangular gravitational wave detector in space with arms of 2.5 million kilometers. And Einstein telescope we saw before. And in between their 2 sensitivity curves is a gap where we think that with the lunar gravitational wave antenna we can make a difference. But of course we need to make seismometers that are at the frequencies that are most interesting there, 1 hertz and a little bit below. They have to be 1,000 times or so better. So we have our work cut out for us. So here you see if we make that happen, what will you see on the moon? So this is a permanent shadow region where we put these seismometers. These of course have to be powered. So one of the options is to have some kind of laser transmission of the power that solar panels here on the edge, where you do have sun, might come in handy. Yeah, this is what we would like to see in I don't know, 10-15 years or so. It gets better because putting such sensitive seismometers on the moon has other benefits. So because of the constant barrage of meteors, you can do prospecting for lunar mining. So the meteors cause seismic waves to go through, they reflect, and you can detect them. Of course, what do you want to see? People think there is swaths of helium-3 and the rare earth metals. Similarly, we can search for ice, and this is good for a South Pole base. And of course, if you want to know more about the inner workings of the moon or lunar geophysics, you can also do that with this. So here's the summary. I think I'll leave the text up. But the only thing I wanted to say is, well, you saw we were working on the interferometric readout, but also the first blocks of niobium have arrived, and we can use them to cut our structures out of and proof mass and frame, etc. So I hope to see you next time you'll see this blog. I hope to show you a more interesting picture. But that's all. Thank you very much for your attention.